So today we're going to cover some of the truth table notebooks that show you how to use the truth data from the DC2 simulation and how to compare it with and how to join it with the DP0.2 object table. So it's going to be me and Jeff today that'll cover that. First, we have a bunch of announcements for you though. So let's go through those. As we're going through the announcements, log in at data.lssu.cloud as usual, go into the notebook aspect and open notebook number 8. And I just wanted to give you in the chat a copy of the slides so that if you need it, you can refer back to the announcements that we're about to make and the instructions, etc. So there you have it. Okay. First announcement is that, as you may have noticed on the community forum, the results of the delegate feedback survey that were done in late 2022 were posted by Gloria. So you can find there a brief summary of sort of the main feedback items that we managed to distill from the survey and a couple of the actions that we took as a result. Yep. So that is there on the forum at community.lsst.org/t. community.lsst.org/t/7402 will take you to the results of the feedback survey. And then I wanted to draw to your attention the fact that there is now the first command line tutorial is up and ready for you. It does the same series of steps as are covered in notebook number 1, but they're done from a terminal instead of from a Jupyter notebook. So if Jupyter notebooks aren't your thing and you much prefer like a Python command line, this is something that you probably want to check out. And you can find it at dp0.2.lsst.io in the tutorial section, just like you can find all the other tutorials. So this is also the first announcement. Well, you saw the first announcement, I think, as a message to you, asking for your input to the first DP0 virtual summer school. So save the dates for June 12th to 16th, either for yourself or for a student that you might want to send. Actually, we have members of our SOC here. If either of them would like to just say a few words about what the virtual summer school is going to be like, maybe Jeff or Ryan.
Sure. Yeah. The plan is for this to be a week-long sort of. Oh, okay. I almost said boot camp, but forget I said that. It's going to be way more fun than that. But it's sort of an accelerated learning experience where you can like go through a bunch of the tutorials all in a week with other people, and then we will have breakout sessions where you can go and work together with other delegates to either further your understanding of the tutorials or to form community and create projects, science projects that you want to do with the DP0 data set. So each day we'll have some tutorials and some sort of breakout hack times combined. And I'll also note that we'll do 2 sessions each day. We'll have the few hours early in the day, my time, Pacific time, for mostly North American audience, I guess North and South American audience, and then we'll have additional sessions evening hour time for that accommodate East Asia, Australia, other time zones. So the idea is to make it available to all delegates. And I don't know if Ryan had anything else to add.
No, I think you summarized that pretty well. Thanks, Jeff.
Oh, the one last thing I would say is we are accepting input, your input. If there are things in particular you would like to see and you haven't filled out the planning form that Melissa just clicked on, do that by the end of today. It should only take a few minutes. and you can help us decide what are the priorities to focus on.
Yeah, it's pretty short form. And let us know too if you'd like to be on the SOC. I put the link right in the chat, so you can go straight to it. Okay, anything else about the summer school? I think you pretty much covered it all. Yeah, okay. The other rather large announcement is that, as you should have seen in a message from me either via email or from the community forum this week, identity migration is happening at data.lsst.cloud. So we're moving from GitHub, which is the current authorization mechanism, which was always meant to be temporary, to CI logon. And so there's a series of actions that everyone will have to take next week, starting Thursday, February 23rd, where you will, if you go to data.lsst.cloud that day, you will be prompted to get a new account. There'll be a banner there with a prompt that'll take you through it. And it's actually 2 stages, very similar to how you got your account in the first place, where first you have to ask for an account using your institutional identity. And then I will see that you've asked for one, and I will cross-match it with our list of delegates, and I'll say, yes, that person definitely has data rights and they can have an account at data.lsst.cloud. That might take a few days if there's lots of people trying to get their new account. So no need to wait. But do this on Thursday, if you can. But it also might take a day or two for me to approve everyone's account. And then when you log in, it won't take you through GitHub to log in. It will take you through your institutional identity provider. So much like when you're logging into your local institutional email and stuff like that, you have some identity and it'll take you that way. Once you're logged in, you can then add additional identities like GitHub. And so in the future, you can, if you want to, continue to log in via GitHub. It's always nice to add additional identities just for long-term logging in so that you have options for your login. So starting Thursday, when you go to data.lsst.cloud, you'll be prompted to take this action to activate a new account. Once you are all set up, you will have a whole new home directory at data.lsst.cloud, but you can retrieve your old files that are currently in your home directory. They'll all just be sort of put in /scratch/old home, and then it'll be your username, and you'll be able to copy all your stuff over into your new account. And those files, so everything in everyone's home directories now will be visible at /scratch/old home until July 15th. You'll also have to reset your GitHub SSH key, reinstall any custom software, that kind of stuff in your new fresh home directory. We'll be definitely offering help with this. So Stat Club on Friday the 24th, which is the next day, drop in anytime. We'll take you through the steps. I can approve your petition live, sitting there right with you, and make sure everything's set up and working right for you. Or the delegate assembly in 2 weeks, we will have a breakout room in the second hour to get you all sorted. So that is coming next week. It should be fairly easy because you should be prompted to do everything that you need to do. If you have any questions, please reach out, post in the forum, send me an email, anything to get you up and started in the new system. Any questions about that right now? Any burning questions? You can unmute or pop them in the chat. Okay, I'm sure there will be questions next week, and that's totally fine. All right. The other announcement is that we bumped the recommended image for data.lsst.cloud to a new version of the LSST science pipelines. This happened yesterday. It's now weekly 2023-07, and as before it was weekly 2022-40. And so all of the tutorial notebooks in your notebooks directory should have updated. They should all have the header that says they run with LSST Science Pipelines version weekly 2023-07. If they don't say that and you have a problem in your tutorial notebooks directory, you can, the easiest way to fix a broken tutorial notebooks directory is to just delete it and then log back out and log back in, and you will magically have a fresh version of the most up-to-date notebooks. That's the easy way. If that's also not working for you because tutorial notebooks directory is read-only and it can't delete, the second fastest thing to do is to just make a new temporary directory in your home directory called My Notebooks, for example, and then git clone the tutorial notebooks into there, and you will have the freshest versions that you need for today. Those will not automatically update in the future, but at least you'll have them for today. So if you are looking at today's notebook, which is number 8, which should be in your notebooks directory, in your tutorial notebooks directory, number 8, open. And if it doesn't say this, it doesn't say weekly 2023-07, definitely grab a screenshot of this and get yourself set up with the latest version. And then we're going to use some other notebooks later as well. And they are in the Delegate Contributions DP0.2 repository. And so if you're not quite sure what that is, we will pause again briefly before we move from notebook 8 to this other notebook to try and make sure you have them, but also just grab a screenshot of this because this shows you, again, you're doing a git clone on this repo, and then you'll have the notebook that I'm going to show you a little bit later. So grab a screenshot of that, but we'll also pause to make sure you get it later. All right, that was a lot of announcements. We're going to head into the tutorial now. So first tutorial is going to be notebook number 8. It's in your tutorial notebooks directory. So I'll give you just a second to kind of get that one open. And Jeff's going to present this notebook, and we'll just pause for any questions or troubles in opening it before we launch into the tutorial. I'm going to stop sharing so I can let Jeff start to share. That looks pretty good, Jeff. I can see your screen.
Sorry, I'm just trying to figure out how to be able to see you all at the same time because it put them both on the same monitor. Okay, there we go. Okay, so today we're going to go through how to work with the truth tables. This notebook is going to go through the ones that have been ingested into the databases that alongside the DP0.2 data set. And then Melissa's going to show you some that are on the same servers but are not in the database. So you'll see 2 different ways to access different parts of the truth information that went into creating the simulated data set. And remember, this is a simulated data set, so it started with some inputs that were then simulated. So if you want to test your algorithm to see how well it's recovering the types of things you want or how well it's measuring things, you might want to compare the measurements from the object table to the known sort of true simulated sizes, shapes, fluxes, etc. So we're going to go through that just a little bit here. This is going to use mostly the tap service, which you're hopefully now familiar with. query and retrieve data, and showing you some table joins that will combine data from different tables. So we'll just start with basics. You'll notice I made a copy of the notebook, and I'm just working in a copy, but I haven't already executed one if things get wonky here. But as usual, we're just going to import some basic packages, matplotlib, some numpy pandas, and then we need the get tap service so that we can do tap queries. And then we're just going to set pandas to only display 200 rows. And then we're going to tell matplotlib to show the plots in the notebook. And then one more action, you may have seen this in other notebooks as well, that we're trying to use a standard set of colors and symbols for the different LSST filters. So we'll just define those here so that when we make plots later, we can just apply the color. If we plot G-band, we can just select that color from this dictionary and that symbol from this dictionary. Okay, so hopefully you've seen in other notebooks the use of the tap service. We've used it in most of the notebooks that we've demonstrated thus far. So the first thing you always have to do is just get the tap service by executing this get tap service function. And now let's go look around and see what's available in the truth tables. So you can do this in two ways. One, you could go to the portal and just browse the list of columns available in each table, which is often really handy as a way to quickly see what's available in each table. But the other way you can do it is from within the notebook aspect. You can just go and do a select description table name from the tap schema, and then just loop over and print each item. So let's see what that does for us. Okay, this shows us these various tables, and you can see here, for example, there is matches truth, and there is truth summary. So now let's go and pick these out and see what exists in those schema. Oh, and I'm just in this notebook, we delete the results, intermediate results along the way if we're not going to need them later, just to save memory. Okay, so in this case, we're going to look at the matches truth. So we want to select just the column name and the description from the schema for this matches truth table. So again, I hope you've seen this in some of the other TAP notebooks, so I'll just do this quickly so that you can see what that looks like. Okay, so this has only a few columns. Unfortunately, it's truncating our results here in this description field. So we can display it in a different way. This is displaying it as a pandas data frame, but you can actually just loop over each column in this and print them with a format string, just to make it easier to read the full text. Okay, and so here you go. Now you can see that this contains an ID for the truth summary source, and then it has an additional ID that this is actually what you want to use to join on, because this combines the truth summary ID and the type of source, and so that makes it a unique result. And then this is just a flag. The match candidate is a flag that just flags sources that were selected to match. This tells you how well the source was matched between the object and the truth table, how many objects matched within the match radius that was applied, and most important, what you're going to need now is this match object ID, because this gives you the ID in the object table of the entry that was matched to the truth summary table. And then finally, you have the truth type, which is 1 for galaxies, 2 for stars, and 3 for supernovae. And then likewise, we can go and look at the schema for the truth summary table, because remember, this is the match, matches truth. So this is the information about matching between object and truth summary. And then this is the actual truth summary table. Again, it truncates our results. So let's print it in an easier to read way. Here we go. Okay, so now you can see this has information about the true objects that were simulated. So it has the fluxes that were input, the actual positions in RA and DEC. It has that truth type field again. It has a flag for things that are point sources and a flag for things that are variable, which can be very handy. It has a redshift for any extragalactic sources. So this is what you'll want to compare measurements to, essentially, in the end. So now we're going to go and actually retrieve some data from those tables. And so you saw in the column description, so in case you forget, you can always look at the schema and see in the column description that it's the ID truth type that you want to use to join these two tables. So let's go through this in a little detail. So this time we're going to call the matches truth table MT here. So we do this as, so we say DP0.2 blah 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 dot matches truth as MT, and then we do truth summary as TS. And so this says here we're going to select ID truth type. We're going to select the match object ID from matches truth. And that's the information we'll need to go and match to the object table. And then from the truth summary, we're going to select the RA and DEC and what type of object each one was. And then we just use this join truth summary on matches truth ID truth type equals truth summary ID truth type. And then we just do a where positional constraint to pick everything within 0.1 degrees of this position. So let's see. That you can see it's executing. Note in the most recent version of the most recent update of the notebook aspect that you get this timing on each cell, by the way. This is super handy. I'm very happy to have this. Okay, so now we can say we've retrieved those. We did the search. Now let's just retrieve those as a table and plot it to the screen. Okay, you can see we got almost 66,000 matches in that 0.1 degrees. One thing you'll note here is, and it is noted here as well, that many of these don't have a match object ID entry. So that tells us that many of the true sources that were simulated were not detected. Maybe they were too faint, maybe, or for whatever reason, they were not detected. And so they don't have a match to the object table. So the next cell, we actually just go in and we say, okay, we have a total of, did I do this right? Yeah. This is selecting, I guess, where you have a match. So this is only selecting the sources where that match object ID is not blank. And then printing the total number and then telling us what fraction of the sources that, or of the true objects have we retrieved with a match. So you can see here, we've retrieved 14,850, and remember it was 66,000 objects. And that is, so 23% of them have a match in the object table. Okay, so moving on now. Now we get to the fun part. This actually took a little while to for me to sort out the first time I did it, because I'm learning how to do these, create these queries as well. This is a triple table join. So you're going to join matches truth, truth summary, and the object table. And so the way you do that here is, remember, we had matches truth as MT, we had the truth summary as TS, and now we're going to also join on object as OBJ. And so again, you see the first line is the same as it was before, but now we're going to also retrieve the RA and DEC from the object table. And so then again, we do the join the same way as before, where we say we need the matches truth and the truth summary ID truth type to match. But then we also say, take that and join it on the object table, where the matches truth match object ID matches the object ID. And this should give us the join of all three of those.
Jeff, can I add an important point here?
Yes, please.
Which is in the notebooks, we are always using an RA and DEC constraint that's pretty small to start out with when we're testing things. You can see here, we're just grabbing things within a 0.1 degree radius. And that's because these queries are very intense. The matches truth table is kind of a special table. And so as you're testing or playing around with the truth data, your life will be much, much easier if you start testing with very small areas of sky, then increase it just until the maximum that you need to do whatever it is that you're doing. So just be warned there that the matches truth table is especially sensitive, and it's best to keep your queries small.
Yeah, and in fact, even this only 0.1 degree, already is returning almost 15,000 objects. So you can even go smaller if you're really just testing things out, so that you don't have to wait. You saw that took nearly a minute to complete. So you can even speed it up by making this constraint even smaller than 0.1 degrees. Okay, but the cool thing here is, notice we got 14,850 results from the triple join, which is exactly the number that we expected. So feels like we did our join correctly. Excellent. Okay. So that shows you how to match things up. In the next section, we go on to show you how to pick out, for a single object, how do you test whether the truth match data exists. And this has a long note, and it is important that the mechanics of the way the tables are created means that if you do the where object ID equals this, you'll get a fairly efficient query. But if you instead did the reverse, because remember, we're trying to pick things where match object ID equals this object ID, but if you do the where on the matches truth instead, it will take a really long time. It can take a really long time. And that's because it's described here. It's because QServe has two different types of tables. There are director tables, which is what the truth summary and the object table are. And then there's the matches truth table, for example, is restored as a ref match table. And so there are mechanics sort of underneath the hood to optimize the queries when you use the where restrictions on the director tables. So you want to do this selection of where object ID equals on the object table. So this will make a huge difference, and we all will forget multiple times and be like, why is my query taking so long? So so try and keep in mind that this is one thing to check for if your query is not doing a great job. And in the future, hopefully we can add tooling to QServe so that it can recognize queries like that and go, oh no, I think what you really wanted was this, but right now doesn't do that. So we're going to be smart about it in the first place. And trust me, this comes from experience of having the experience of waiting forever and being like, well, what's going on? Okay, so that aside, what we're going to do is we're going to pick some object with this object ID. So if we go back up here and look, here's what those object IDs look like. They're a long string of numbers. So we're going to pick one of them that has this address, this number. So you can see that number here. And so now we're just doing, that same triple join where we have the matches truth as MT, truth summary as TS, object as OBJ. And instead of that spatial constraint that we were doing before, this time we're saying the where statement instead of where RADEC is within this circle, we just say where the object equals this value. And we also include truth type equals 1 and detect as primary equals 1. May not be necessary. You'll see, because there's only one object. Actually, I don't recall. If I do this instead, we're going to test it. Okay, yeah, I actually would only get the one, even if I left out those constraints. But anyway, so now you say, okay, this object has been detected, or that I have detected is in the truth tables. That's very helpful. So now we want to go and just do this for multiple objects, for true galaxies that are matched to objects we've detected in the object table. So remember, we're using galaxies here. So instead of using the PSF flux, which is good for point sources, we're going to use the C model flux. That's a sort of a galaxy model. So we'll use that. Down here, you'll see the C model flux. There's also a note here, which is important for you to remember, that when you see how we've included in all of the names, we've included MT underscore ID truth type and like TS underscore RA. And that's because if you don't include that, you'll get back a table that has what you want, but you won't know which of the three tables that you joined that each column came from. So for example, you'll have an RA, but you won't know if that came from the truth table or from the object table. So you want to, this is just a helpful way of knowing exactly where you took each piece of information from. Okay, so in this case, we're retrieving more columns than we did before, but this is otherwise the same sort of triple join that we were doing before, where we're joining things within 0.1 degrees of this position, and we're adding here truth type equals 1 so that we only get galaxies, and then things that we know were simulated as galaxies. Remember, these are the truth info. And then from the object table, things that have reliable measurements, basically. This detect as primary, you've probably seen a few times. So this is going to get us all this information about a set of galaxies. So we'll set that going. Actually, that doesn't set it going. That just creates the query. Now we'll set it going while we talk. So while that executes, I'll just point out. So we're retrieving here the truth summary fluxes. So the fluxes that were simulated. And we're retrieving the object table fluxes. So the measured fluxes. We also return an R magnitude. Remember, we can use this function so that it converts the flux to magnitude for us. We're also returning things like the extendedness flag from the object table. Let's see how we're doing here. We're still executing. I'm going to go ahead and execute this cell too, so that once it appears, it'll go ahead and print for us. Were there any questions while we wait for this query to execute? I forget. It takes maybe a couple of minutes.
Yeah, there was one. I think I got it answered though. And it's if you do accidentally start a query that's taking too long, or then you realize, oh, that's not what I wanted to do. You can go to kernel and interrupt kernel, and it'll stop the query cell that's executing. There'll be a big pink error message, but at least you don't have to destroy the entire kernel and go all the way back to the top and re-execute things.
Yeah. Yeah, and I think that's what the stop button here at the top will do as well.
Oh, I never used those buttons. Yeah, okay.
Yeah, I'm pretty sure that will also interrupt the kernel. Interrupt the kernel. There we go. It took a minute for the tooltip to appear, but there we go. Yeah, so okay, so that took about a minute 40. Not bad. And now you see we have our table where we have the object IDs, RA deck, some truth information, and then let's see. And then we have a bunch of information from the object table as well. So now we can get down to some science. We're going to use those and make some plots just to examine what we've gotten out of this. So the first thing we do here is just check how well did we measure the positions of these galaxies. We can just compare the RA that we measured in the object table to the RA in the truth summary, and same for the declination. And these are plotted. You see the 3600 times the difference because those are RA and dec in degrees. This is converting to arc seconds because hopefully they'll be really close to each other. And thankfully, it looks like we did a good job of measuring things. There is zero mean offset, and you can see there's some scatter, but it's really like mostly within 0.1 arc second. So that's a really good confirmation that we've got the right sources and that we're measuring their positions well. You might ask some other questions. The next one that we do here is we use this ref extendedness column, and what this tells us is that this is a classifier that the science pipelines creates to it's basically either 1 or 0. It's set to 1 if the source is measured to be extended, meaning something like a galaxy, and it's set to 0 if it's a point source, if it's not extended. And so we're gonna ask the question, how many of those true galaxies, remember we retrieved them as things that were known to be galaxies that were simulated, how many of those true galaxies actually got classified as being point sources? And so the way we do that is we just select, X here is saying, give me the ones where it said ref extendedness equals 0, meaning the pipelines thought it was a point source. And then we'll just see the number of those and the fraction of those that we picked out. So we picked out about 2,800, and remember we had some, was it 14,000 objects in our table? I lost track of where that went. And so about almost 20% of them were actually misclassified as point sources. This isn't necessarily, indicating anything wrong. Basically, when you put a galaxy, especially a very compact galaxy, far away, it's just probably going to look like a point anyway. So, so you can explore, like, yeah, are there galaxies of different morphologies or colors, or is it mostly just a function of magnitude? Are they more distant? Which ones are misclassified? So as we noted here, it's left as an exercise for the learner. But yeah, that's something you could explore if you wanted to know more about, like which ones does it do a better job of identifying and which ones not so much. Another thing we can do here is we can compare remember we extracted the R magnitudes for all the galaxies. We can compare the measured to the true R band magnitudes. And note here that we select galaxies by using that ref extendedness 1. And then in the second, the black points are ref extendedness 0, the point sources. And so you see here, this is the 1-to-1 line. You can see that we've recovered the magnitudes pretty well for most of these objects. And actually the ones that are point-like you can see here are mostly at the faint end, as you might expect. And so then we go on here to do the same thing to compare the fluxes instead of the magnitudes, but do a similar comparison to that previous one in all of the flux bands that we've extracted. And so this just shows you that comparison in U, G, R, I, Z, and Y. Here, I'll go down so you can see. So this is just the true flux and the measured flux. And you see it mostly hugs that 1-to-1 line. And if you're interested, you could go and explore the ones that are outliers. You can see most of them are low flux, so they're just faint. Okay, and finally, just another demonstration of a comparison you might want to do. We can just look at color magnitude diagrams for the true properties that were simulated and the measured properties of each galaxy. And so this shows you here this is what it should look like if you had perfect measurements. So this is the true simulated magnitudes and colors, and this is what you get back, which you can see the effects of measurement errors spreading this out at the faint end and things like that. And then we can do the same, but for the I minus Z color. So you're measuring a color that's independent of the magnitude axis, and we'll do something like that. And again, this is what we expect if we were recovering everything perfectly, and this is what we get, which looks pretty similar, but you can see in the features it looks pretty similar, but you see the effect of the photometric errors spreading things out. Okay, so there are many other things you could explore, obviously. This is just to show you sort of how you could do that exploration. There are, you can also explore stars. You can explore supernovae because we have the truth type flags for those. You can, explore different types of galaxies and how their measurements perform, and various other. I'm sure you can think of many things, but I want to leave time for Melissa and take any questions if you have them.
Excellent. Thank you, Jeff. We've had some questions as you were going along.
Oh yeah, I see 13 of them. All right. We can also come, if there are any questions, we can also during the breakout time field any other questions that you have. But now I think Melissa was going to show you some other truth information that is beyond what is available in the TAP service.
Whoops. Hold on. There we go. Let me just get set up here. Get my chat back. Everything is ruined when you share your screen. Nice setup. Everything like shifts around. Yeah. Okay, here we go. Right. Okay, so the notebook I'm about to use to show you how to access additional DC2 truth information is not in your notebooks/tutorial notebooks directory. It's in a separate repository for delegate contributions. So I'm going to just show you how to get it in case you don't have it at all. So if you're probably here, you're in the notebook aspect. First thing you want to do is click on this blue plus up in the upper left corner, open a terminal window, go to your home directory using the CD command. I already have a my_notebooks directory, but if you didn't have one, you could make it with make_my_notebook. Like so. Put that in the chat. And then you go into it. Like so. I have lots of subdirectories in here where I do my work already. I already have the delegate contributions DP0.2 repository, but let me show you how to get that. You would start at github.com/ruben-dp0, which is our GitHub organization for DP0. You go into the delegate contributions-dp0 repository. So you're starting from here. That's the link. In here, there's this green code button. You can press that code button and it gives you sort of like the URL to do a git clone on this repository. So you would copy what you see there when you press that green code button, go back to your terminal in the notebook aspect, type git clone, and then paste that thing that you just got from there. Also going into the chat. And after you do that, there'll be a couple of lines that say, okay, I'm downloading all the contents of that repo. It would look like this right here, where you're cloning the repo. It's telling you that it's doing it. And then once you've done it and you ls in this directory, you will see the delegate contributions DP0.2 repository. So now you want to open a notebook that's in that new directory that you just made. So now you're using the left sidebar, go to home, just click on the file there. You want to go to your My Notebooks directory that you just made. You want to go to Delegate Contributions DP0-2 directory that you just made. And today we're working in the desk_truth directory. So you would go into there. And then there's only one notebook in there, and it's the read truth parquet files notebook. So you would open up that one, and it should look like this. So that is how to get today's notebook, how to clone a GitHub repo, and then how to open it once you do have it in the notebook aspect. Any questions or problems with that? Okay. So this particular notebook shows you how to open and use the data, truth data from the Dark Energy Science collaboration that is in Parquet files. These are extra sources of truth information. There are 4 files that Jim Chang has made available for us. One has is a summary of the supernovae. One has the actual true supernova light curves in it. One is a summary of the variable stars that are in the DC2 simulation. And one has the actual truth values for those variable star light curves. So you can notice right away that this star variability with the actual true light curves in it is very large. So 5.3 gigabytes. All of these other 3 tables, these Parquet tables, Parquet is just a format. This is just a file format. Parquet can be read directly with the pandas package in Python. And so these first three files are small enough to just be read in directly with pandas, but you do need some specialized packages for extracting data from this massive file. 5.3 gigs is too big to just sort of read into a Python array. So we have to do things a little more specially. These tables are DC2, so they are from the simulation that Desk made. They are not matched to DP0.2 detections in the images, and they will not be matched at all. So if you want to use the additional truth data for anything that you happen to be doing with the DP0.2 detections, then you have to do the matching yourself. And this notebook is going to show you a little bit about that. And in a breakout, I can show you a couple of other notebooks that do this kind of matching should you need it. So if you want to know more about what is in these Parquet files, these tables, you should look at the Desk's DC2 data release note, which is available. And in particular, there's appendices, which basically have the schema for these DC2 files that have been released. So let's start off and import a bunch of packages that we're going to need. I mentioned already pandas that can be used to read Parquet files. And then there's 2 other options, PyArrow and Dask, which are both packages, Python packages that do a lot of other things. But the handy pieces that we're going to use out of PyArrow and Dask are their ability to pick out pieces or pick out data from a Parquet file and load it into your notebook. So first, I have some examples of extracting star truth data. First thing we do is just set up the file paths and file names for these Parquet files. Get them set up. And then, as I mentioned, the star summary file is small enough to be read entirely with pandas. So you can do this in one line and just read it, the entire star summary file in. Like so, pretty quick. I'm going to uncomment this. And if you just want a quick look at what is in this star summary table, there you go. And so basically that gets you up and running with the star summary table. If you want to, what is this doing? Identify a single true star of interest. Right, so in the star summary table, there are like types of variable stars. The Desk DC2 simulation used 3 types of variable stars, basically the periodic variables, non-periodic, and then some stars that were simulated basically based on Kepler light curves. So let's take a look at how many of each type there are. So this just did, just use the numpy.unique function to say how many of each type are there. You can notice, for example, there's only 211 RR Lyrae stars that were simulated in DC2. We could, for example, say, okay, I'm only interested in RR Lyrae stars, print me the ID and the RA index of all of one random RR Lyrae star. So if you're interested in those, you can interact with this data file that you got from Parquet in this way. If, for example, you are off using the DIA objects measurements and you said, oh, hey, this star looks like it might be an RR Lyrae star and I have its RA index. Now I want to go to the truth tables and see if it really was an RR Lyrae star. You can start with the RA index that you got from the DIA objects. And then you can say, is there an RR Lyrae star from these special truth match tables at that location? And there you can get the the truth table ID for that RLI star, and then you can get like the other truth data that goes along with it to continue your investigations. So that is one example. Okay. So as I mentioned before, the star variability table does have the true light curves in it, but it's too large to read. You can't just like read in the whole thing and then deal with the data in that table. So this is an example of how to use the package PyArrow to retrieve just the true light curve from the star variability table for this one RLI ray star that we think is interesting. So the science workflow here is you were in DIA objects, you found something that had like an interesting light curve, you thought, oh, that maybe is an RLI ray. You go to the truth tables, you say, yes, there was an RLI ray truth star at that location. Now I want to get its true light curve so I can compare it to the light curve that the LSST science pipelines got for it. So this line, it basically, you give it just the ID value that you want out of the parquet table, and it goes in and it only pulls out the true light curve for that particular object. So we can do that. Just going to take a few seconds. No, why? That's abnormal. Oh, you too. Interesting. Oh, like totally restarted. Okay. Let's get back on track. That should not be dying like this. This is not large. We don't need a special container. Is anybody else able to didn't see one person. Yours is still running. This does not usually happen. And I tested this file this morning and it ran fine. So I don't know why my kernel keeps dying.
Mine died.
Everyone's is dying on this now, but it wasn't.
It's weird though,
before.
because I had it open from yesterday afternoon when I was going through that notebook, and I just executed that, and it took like a couple of seconds and executed fine.
Yeah, then I don't think it should matter that we're all trying to do it at the same time. Same error. Maybe it is because we're all trying to do it at the same time, because that's the only thing that's different from when I ran it like an hour ago and it didn't care. Interesting. Okay, I will check with people to see. So we're all getting the same error and all trying to run it at the same time. All right. I think I'm just checking for, I don't think we have any science platform developers here with us today. I'm going to check with them about this issue. Okay, everybody stops their kernel. And then only me tries to rerun it. Maybe I can at least show you that it works. So if everyone, you go to restart kernel and clear it outputs. Let it settle. And now just I will try. Okay. Oh, thanks, Jeff. Yeah, if you want to report this on our behalf. Oh, new error mode. Okay. Well, we'll get this figured out later. But that's not, shouldn't be happening. So maybe we're learning something about parquet tables. No, I don't think you need to log out. Or definitely don't log out. When you did interrupt kernel, it kept running for a little while. Interrupt kernel might have kept running. Maybe you have to restart the whole thing and clear all outputs.
Hey, I reset my container to large and it looks like I ran.
Oh, really? Oh, I did say that we should be using a large container for this, but oops, no, don't move. No. I thought that was for a different reason. I wouldn't have expected it to need a large container to only take out one thing from the star variability table.
Nice plots, by the way.
What's up?
Nice looking plots that come out.
Oh, okay. Oh, Bob, do you want to share your screen and show us what it looks like when it works? Just real quick, and then we'll
Let
end.
me, oh,
Is it
gotta get
possible?
permission.
Oh, how about now?
Okay. Just a second, let me. Do you want me to just move through it as you?
Yeah, just show the plot that comes out, the just one true light curve for the RLI ray. Just the
Okay.
first one. Yeah.
Is that the?
So, yeah, exactly. So if it had run and then you would get the true light curve for one RLI ray star, it looks like this. In notebook 7B for the tutorial notebooks, one that Jeff has written. Jeff, you wrote a, what's it called when you get the period? What's the process called?
Ramskarl-Pyadogram.
Yeah. So you can look at notebook 7B to find the period for that, and then do like phase folding and make a proper RLI ray light curve. But that's what it would have looked like if we pulled out one true light curve. So thank you, Bob. We will stop tutorial part there.